In the Tuesday class, we derive the solution of small amplitude water wave theory, right? We specified the governing equation, which was a Laplace equation, and also we specified the boundary condition in the free surface at the bottom, and also we specified the lateral boundary condition in left side and right side. The solution for the progressive wave. So the unknown was a potential, right? So if we take the gradient of the potential, we can have a velocity of a fluid particle. This is a solution for progressive wave. Hyperbolic cosine kh, hyperbolic cosine h plus g sine kx minus sigma t. And also, we derived a very important relation. It's named the dispersion relation, GK, hyperbolic tangent, KH, with sigma equal, sigma is a frequency of the wave, and K is a wave number. So sigma is a frequency, it's about time, and wave number is about space. And this dispersion equation, dispersion relation, give us the relationship between the sigma and K, right? And also water depth H. We define the shallow water when water depth over wavelength is 1 of 20. We are saying this is a case of shallow water. In this case, we can have a speed, wave speed is gh. So in shallow water case, the wave of speed is only function of water depth. Okay? So when the water depth is small, speed becomes smaller. Okay? Then in deep water case, we define the deep water case when h over l is bigger than 2. In this case, we have a dispersion relationship become sigma square equal gk. So about the T and L, let's put this equation over there, that equation over there. We're gonna have a t 2 pi t square equal g L 2 pi tangent kh, right? Then then 2 pi here disappear, square, so L become g t square 2 pi tangent kh, right? This is also dispersion relationship. Here we don't, we have L and T. Yes, hyperbole, sorry. In deep order case, L0 2 pi gt square. L0 is a wavelength in deep order case. Okay, so if you put this here, then you're gonna have L equal L0 tangent kh. It means the L0 is a wavelength in deep order case as the water depth decrease. Okay, wavelength also decrease. So I mean here we have a deep water. This is a deep water. And here shallow water. We have a same wave. As wave go to the shore, the wavelengths become smaller and smaller because the depth becomes smaller and smaller. And also similarly we can derive C0. We can define C0. C0 equal GT 2 pi. Here if I divide by T, if I divide this equation by T, we're gonna have a wave speed T, C0, and C will be a C0 tangent kh. So as the water depth decrease, wavelength decrease and wave speed also decrease. Okay. Okay, that property of water wave. Now let me talk about another property. Let me talk about property of progressive wave. Property of progressive wave. So we have already the solution of progressive wave. I mean we have a potential function for progressive wave, right? It's given. Then we can calculate particle velocity. U x, right? And W going to be a minus G. This is the velocity of the water particle. This will be your H sigma 2 sine hyperbolic sine K H cosine hyperbolic cosine K H plus G cosine Kx minus sigma x here 2H sigma sine H K H sine H K H plus G sine Kx. Okay, this looks very complex. How about the velocity vector in 2D UW? Then we can plot this velocity vector. G and X. This is the mean water surface, x-axis, and we have a bottom here. So let's assume we have a wave like that. Okay, we can plot this vector at here. This is your point x equals 0. Just put the x equals 0 here and here. Then here we don't have a sorry, here this should be k sigma t, right? Sigma t. So for some given time t, if we put the x, we only have a wave component in x direction. So here we have a maximum velocity here and minimum velocity here. This is a wave profile along the axis x equals 0. Along this axis, we don't have any wave component in g direction. So we have only particle velocity is always the x direction, and here similarly we can calculate. Here also we have only velocity. This is the reverse direction. When the wave direction is this wave direction. Okay, and this point, our wave direction is upward, and its magnitude becomes smaller and smaller as the g decrease, and here reverse. Okay, so then how about here? Maybe here. There are going to be components in x and y both. Maybe something like this, right? Maybe in here we're going to have a direction, wave direction like that. So that's the velocity profile of progressive wave. Okay, Then let me look at how the water particle move as the wave move. This is Gx. Let's say this is a wave at this is wave direction, wave at time t1, and let's see the particle here. We have a particle here. What's the wave direction? In that position. Here. This one. Right? So we're gonna have a wave the direction downward, right? After some time t2, okay. Let's say this is a time t equal t2. As time goes from time t1, t2, so wave the profile changed. So just look at the red graph here. Then what's the direction of the wave? Here, that is this point. So we're gonna have a particle velocity in this direction, right? Then let's look at one more. Then also we're gonna have a wave like that. Then what's the direction here? Look at that. Yeah, we are in this point. So in this line, then we have a wave direction in here, right? This is let's say this is T3 and T4. T4 going to be a situation like that. This is T4. T equal T4. We are here. So direction change like that. Then then we can assume the how particle move. So particle first move downward and then go to the left, go up. Sorry, it's going this way. Go to the x direction. And there are going to be some transition area here. No. Right? Something like that. So you can know that our particle moving like a circle. Right? That path of the particle movement can be calculated by integration about the time. This is a particle trajectory. in extraction, if we take the integration about the t, this will give you minus 2h sine h kh hyperbolic cosine k h plus g and sine kx minus sigma t, and particle movement in g direction t h over 2 h k h plus g sine h k h cosine k x minus sigma t, right? So here the let's this is A, this is B. Then we are going to have a equation minus A sine kx minus sigma t, B sine cosine kx minus sigma t. And we know that the simplification sine square theta plus cosine square theta equal 1. You know, if you put this to here, you're gonna have a too warm. Equation A square plus B square plus equal 1. What's this? Huh? This is a equation of ellipse. This is ellipse. Okay. Radius A, radius B. If A and B is the same, that means the circle, right? We are saying that's the particle trajectory. This equation shows you how the particle moving in the water body. Okay. Let me see the two extreme case, shallow water case and deep water case. I'm gonna give you just the result. I don't know. This is a shallow water case. We have a very long wave. We have a wavelength L. This is a H. Water depth and deep water case. deep water. R H deep water. In shallow water case, A equal 8t 2 pi root g over h, and B equal 8 to 1 plus gh. In deep water, A equal B equal h to ekg. So look at the A. A doesn't depend on the G direction, right? A is this length. And B is this length. B is decreasing. So what happened is that here we have a movement of particle like that, and as you go to the sea bottom, this ellipse become flat, but here A doesn't change, okay? But in deep water case, A and B is equal, so we have always circular motion, but the motion of radius becomes smaller and smaller, right? Smaller and smaller with some function. Any question? Exponential? Here, actually, the first direction for the G is here, right? This is a minus G direction, so at this point, this will be a minus KH, something like that. So, decrease. AB is decrease. Then what happened in the pressure field? So it's good to investigate the pressure field. Pressure field. We know the Bernoulli equation. P plus rho plus 1 over 2 U square W square plus G equals. If we assume the velocity is very small, okay, then we can get rid of this term. Then we can have pressure P equal rho Gg plus rho partial T. Right? This is the pressure. So in this potential, if we put the solution, we're gonna have a P equal minus rho G plus rho G. This is the surface function, and K P G. With Kp is a function of about G, Hk H plus G KH, right? So our water pressure has a two component, minus rho Gg and this one. What's this? And this. This is just hydrostatic pressure, right? This is a hydrostatic pressure. Even we don't have a wave on the surface, we have always that pressure, right? Then this is an additional term. We are saying this is a dynamic pressure. Dynamic pressure, okay? So G X. Let's say we have some point, some line here. We can calculate the pressure along the line. Okay. Hydrostatic pressure is 0 when G is 0. So here hydrostatic pressure is 0 and linearly increase. This is a hydrostatic pressure, and dynamic pressure will be a function of hyperbolic cosine, right? If I plot, it's something like that. It decreases. So sum of these will be a total pressure. This is a hydrostatic this is dynamic pressure. Okay, this will be a dynamic. The wave direction is this one, x direction. So from the given solution, which is potential, we calculate the particle velocity and trajectory of the particle. It's a path of the particle, and also we calculate the pressure field. Now let me talk about energy. usually there are two kind of energy here. Here, what kind of energy we have? Two energy. Potential energy and kinematic energy, right? Energy. You know, there is just some pond. I mean, there is some still water here. If you put some stone into the water, it will make some energy, right? So it will give you some wave, and that wave will propagate, right? It means there is going to be some energy transmission from this point to the other point, right? Let me talk about that. That's the energy propagation. Energy propagation. Wave of water, wave, and its length is L. This is the bottom. H. Wave height H, big H, and small h is depth. This is extraction. X, G. And we have in Gx, this X and G direction, this two-dimensional wave. But in 3D, we have one more direction, Y. So we should assume in Y direction, the wave is uniform. I mean, doesn't change the shape in Y direction. Then, regarding the unit technique, let's consider unit with unit in G. In mean with it's just 1.0. Okay, we are just considering unit band or some length of the wave in G direction. Let's consider only that. And let's calculate the potential. Potential energy. Here, let's say we have some water column here. Its width is a differential dx. At this point, we have a column height x and t, right? And let's say this is a gravity center of the water column, right? The gravity center is defined by here G bar. Then our potential for this area, let's say that is a d PE will be a dm g, right? Actually, potential is mgh, right? So this is mgh, right? And dm is a mass of that volume will be a rho multiply h dx multiply 1, because this gives us a volume, right? And center of the gravity center will be a h plus over 2, right? Let's put this over there. Let's integrate this potential energy from here to here for the one wavelength. That means PE equal from some point x can be a 0 or more, can be anything, dPE. And let's take average. This is averaged potential energy. Because average means we take the length L, it means average. And this is a total average potential energy, total. If you solve this equation, put this will be a 1 over L x plus L. Let's put over there x rho 2h square dx, right? Then this is the equation which everybody can solve. This will give you rho g h square 2 plus rho g h square. Here big H is a wave height over 16. What's this? What's this? This is a potential energy when there is no wave, right? This is average potential energy without wave. And this is average potential energy with wave. This is additional potential energy due to the wave. So, no, not with wave, it's due to wave. Due to wave. Okay? So, if I only consider the potential energy due to the wave, let's say that is a wave equal rho g, right? Now you calculated the energy. of potential, the wave. We have one more energy, kinematic energy, right? Kinematic energy. Kinematic energy, dKE, will be a dm and velocity. We have velocity in two directions, x and g. So, and we need to take 2. You know the kinematic energy is Ke 1/2 mv square, right? From here we have this. Here we have a dm, right? This is dm. We know how to calculate the u and w, right? It's a velocity. It can be calculated from the potential. If we take the derivative about x, that's going to be a u. Take the derivative about g, that's going to be a velocity in g direction. It means it's w. And let's calculate K E Ke will be a minus h from the bottom to the top surface, rho u square plus w square to dg dx. And yeah, let's calculate the potential energy, average potential energy, about one wavelength, x2, x plus L. So take the average, 1 over L. Okay, this will be our potential energy. And if we calculate the energy, that become 16 rho g h square. In the still water, we don't have any kinematic energy, right? So that's the only the kinematic energy due to the wave. So we calculated two energy, kinematic energy and potential energy due to the wave. If we sum both, that's going to be a total energy, right? Yeah, not 16. Yeah, right. Same. Both energy are same, right? So let's calculate total average energy. Total energy will be a total average energy E K E plus P E 1 over 8 rho G H square. Right? This is a total average wave energy of progressive wave. Right? Then now let me talk about the energy flux. It means energy transmission. Energy flux is that work done by the dynamic pressure in the water direction, right? Energy can be calculated by force multiply distance, right? So dynamic pressure. In the water we have a dynamic pressure. So actually the pressure field was rho Gg plus rho G and surface function Kp. This was a dynamic pressure. Let's say that's the PD, right? Then what's the water direction? Direction of the water is the wave direction, x direction, right? For that direction, our velocity is u. Then flux is we can calculate the flux for the unit wavelength. We need to calculate pressure. This is a force multiply u. U is a velocity. So flux means the energy transfer rate. Energy multiply T. Each unit is the energy divided by. So you know that energy equal force multiply distance, right? But here this is a force multiply distance. This flux means time. So this is the energy over time. Okay, rate of energy. This time. So here you can calculate, we already know this dynamic pressure and U from the solution. Then let's take that integration and take average flux. Average flux means average for the period from T to T, from minus H to P du dg dt. This is the average flux. If we calculate this flux, we're gonna have a ECG with CG equal 1/2 1 plus 2kh y public sign 2k x c. C is a wave speed, right? Or we are saying just this n c. This is n. And CG has a unit of speed, right? It's a kind of speed. We are saying CG is a group velocity. Right? Physically, group velocity means the speed at which the energy is transmitted. Right? Group velocity is the speed of energy transport, right? Okay. Energy to propagate with that speed, CG, group velocity. Transmitted. So, to this point, we only consider 2D case, and we only consider just one wave, single wave, right? But in reality, our wave not have that single. So, actual wave is a sum of the lot of wave. I mean the actual wave so we only discuss single wave, simple sinusoidal single wave, right? But in reality, wave is not that single, so I don't know how something like that, right? This is a sum of lot of wave. This wave plus that wave plus maybe this wave plus, right? This is a real wave is like that. Then what's going to be our solution for that kind of wave? So surface function. Yeah, let's just consider surface function. Surface function for single wave, surface function of h/2 cosine kx sigma t. Right? We are going to have a lot of wave. Let's say sigma I equal to that wave will have a different height, wave height, and also different wavelengths, wave number x minus different wave frequency I and t, and also the start point of the wave will be different. So I mean, though, we need to have some page, let's say that's n m, okay. Then we can get a wave like that, sigma I plus 1 to n hi cosine ki x sigma I t, right? Actually, this is a kind of a random process, but I don't know very well about that. So this is the end of the lecture about the wave mechanics. Okay, so this is another full semester class. So I think I just give you some knowledge, maybe concept of wave mechanics. You know, I reviewed the fundamental of fluid mechanics and drive the small amplitude theory, and we looked at property of waves. Maybe in other class by Professor Choi, he's a real specialist on the wave mechanics. Maybe he will going to touch everything in detail. Okay, you'll have that wave mechanics class in this fall semester. So if you want to know more detailed theory and fundamentals and application, then you should take that class. Okay.